Before we begin, let's get acquainted with our hero, Euler's totient function, phi of n. Phi of n counts the positive integers from 1 up to n that share no common factor with n other than 1, of course. For instance, when n is 6, the integers from 1 to 6 are 1, 2, 3, 4, 5, 6. Of these, only 1 and 5 are coprime to 6. So, phi of 6 equals 2. When n is a prime, like 7, every integer below it is coprime, so phi of 7 is 6. Got it? Then let's ask the real question. How small can phi of n get? On primes, it's almost n, but pile up enough small primes, and phi shrinks. Today, it can never shrink faster than n over log n. The constant? 3 over pi squared. Two functions of n, phi counts the integers up to n that are coprime to n. Sigma adds up its divisors. For 30, phi is 8. Sigma is 72. Hold on to those. Divide sigma by n, and the divisors flip. It becomes a sum of 1 over d. Throw in every integer from 1 to n. You get the harmonic sum. The integral test caps that at 1 plus log n. So sigma over n grows at most like log n. But why products in the first place? Both phi and sigma break apart across coprime factors, so it's enough to know them on a single prime power. At p to the k, phi counts the integers from 1 to pk that are not multiples of p. There are pk 1 multiples, so phi is pk minus pk 1r, which factors as pk times 1 minus 1 over p. Sigma is the geometric sum, 1 plus p squared, on up to pok. Glue these back together over the prime factorization of n, and out fall the products. Now the trick. Phi over n is a product over primes dividing n. Sigma over n is 2. And look carefully. Each factor shares the same 1 minus 1 over p sitting in the denominator. Multiply phi by sigma, and those cancel. On 30, every prime appears once, so the exponent is 2. Plug in 3/4, 8/9, 24/25, 576 over 900, and 8 times 72 over 900, same number. Every factor is less than 1, so we can drop the exponent, bound it by 1 minus 1 over p squared, then keep dropping. Throw in every prime, even ones that don't divide in. Each new factor is less than 1, so the product only shrinks. But why should pi appear? Watch this. Each factor is a geometric series. 1 over 1 minus 1 over p squared equals 1 plus 1 over p squared plus 1 over p to the fourth, and so on. Multiply those out across all primes, and by unique factorization, every positive integer appears once, the sum of 1 over n squared, and that sum is basal, pi squared over 6. So our product is its reciprocal, 6 over pi squared. Now stitch it. Phi sigma over n squared is at least 6 over pi squared. Solve for phi. Sigma over n is at most 1 plus log n. Substitute. For n at least 3, that's less than 2 log n. The 2 cancels with the 6. 3n over pi squared log n. Sanity check on 30. The bound says phi is at least 2.68, and phi of 30 is 8. Two old inequalities, one little product, a constant from Basel. Phi can never get small fast,